Nikhil and Ritika, only you two are there. I'm just waiting for others to come. We'll just start in 2 minutes if they have not come, because I'm going to start a new chapter and this stuff.
Yeah, okay, sir.
Now we'll start chapter 10, wave optics. So last chapter we discussed that optics is basically classified into two types. What are they? One is called ray and the second is called wave. So you deal with light as a wave when it is interacting with objects whose size is very large compared to the wavelength of light. Whereas in the case of wave optics, what will you do? You will deal with light as a wave when it is interacting with objects which are comparable to the wavelength of light used. Basically, it is wavelength of light itself. Okay. The next point is, what are the topics which are covered in this chapter? First, we'll be discussing about the theory, wave theory of light. Then we will discuss about the concept of wavefronts. Third, we will discuss about principle of superposition. Fourth, we will discuss about Young's double slit experiment. It's called YDSC. And the fifth, we will discuss about a concept called as diffraction. Okay. So we'll first start with the wave theory of light. So before we discuss about the wave theory of light, the first thing that we need to understand is the nature of light, which was proposed by two different scientists, where one of the scientists was Newton and the other scientist was named as Huygens, or you can call it as Huygens also, however you want to pronounce. Okay. So the point that is to be noted here is Newton proposed a theory called as corpuscular theory. So that is the first point you will be discussing about. Means today we know that light has both wave nature and particle nature, but in the 17th century, if you observe, they didn't have much clarity about it because it was not experimentally proved or something. So whatever Newton told was accepted blindly. So Newton came up with the concept saying that it is light behaves like a corpuscular, means it has only particle nature. So at that point, the concept of wave nature didn't exist at all, right? So what he proposed is that light consists of tiny particles called corpuscles, which are shot out at high speed by a luminous object. Okay, and this corpuscular theory could explain certain phenomena like reflection, refraction, and rectilinear propagation of light. So when did this happen? 1675. Okay. And the next theory is the wave theory of light. In 1678, what happened? That scientist named Christian Huygens, what he did is, he suggested that light travels in the form of longitudinal waves. But actually, what is it? In today's world, we know that light is a transverse wave. So he told that light travels in the form of longitudinal waves, just as sound propagates through through air. He also proposed that light waves propagate through all pervading hypothetical medium, and those mediums were called as luminiferous ether. That theory was discarded later. Okay, that theory didn't get supported. Then what happened is, then the rivalry started, then the contradiction part started. Is it having particle nature or is it having wave nature? So what happened is, it had both the natures, but there were certain natures which were useful to help certain phenomena. Means particle nature could actually explain both reflection and refraction, but there were certain observations that were done at later point of time, like concepts of diffraction and interference, which could be explained only using wave theory. Then what happened when this concept came into picture? Again, people started believing that light was completely wave. Then came the concept of photoelectric effect, where photoelectric effect again proved that it had particle nature. So what was the conclusion? Okay, for interference and diffraction, you're saying wave nature existed. For photoelectric effect, you're saying particle nature existed. Then what light is exactly? That is where we say light has dual nature associated with it, which we say it has both wave nature and particle nature, which comes into existence depending on the activity or experiment you're trying to perform. Breather. So it was experimentally proved. See, Fresnel and Young showed that light propagates as a transverse wave. First point to be noted. And secondly is, this successfully explained the concept of reflection, refraction, as well as interference, diffraction, and polarization of light waves, which particle nature could not explain. Okay. Shall I proceed? Now see. Then in the 1873, what happened is, the other theory came, that is the electromagnetic nature of light waves. Who proposed it? Maxwell. So Maxwell suggested that light propagates as electric and magnetic field oscillations, and these waves were called as electromagnetic waves, which require no medium for their propagation. Also, one more conclusion that that was taken into consideration is, he also said that light travels as a transverse wave. Okay. Then the fourth theory that was proposed was Planck's quantum theory of light. So what does Planck's quantum theory state? According to Max Planck, light travels in the form of small packets of energy, that is called bundle of energy, called as photons. You've heard this word. So in the year 1905, what happened is, Albert Einstein, he used this theory to explain the important phenomena called as photoelectric effect, which is basically emission of electrons from metal surface when light falls on it. Am I clear with this point? Yes or no? Shall I proceed?
Yes, sir.
No. So next comes the concept of wavefronts. So you have to imagine this. Suppose you have a still water, right? Then you take a stone and drop it into that still water. What is it you're going to observe? You can observe that there will be ripples formed. I think I've already shown the simulation during electromagnetic waves. So you have circular kind of structure that is formed, where these ripples start traveling in the form of crest and trough, right? So they, if this is the still water, you drop the stone here, there is a point of impact. From the point of impact, the energy starts spreading in circular patterns, right? So that is happening with respect to a medium called water. Now the question is light also going to have something of that sort? Is what we need to understand. Okay. So what he's trying to say is, circular patterns of alternate crest and trough begin to spread out from the point of impact. Clearly, all the particles lying on the crest are in the position of their maximum upward displacement, and hence they are in the same phase. Similarly, all the particles lying on the trough are in the same position of their maximum downward displacement, and therefore they are also in the same phase. Meaning, if you know what is a phase, so you can see there is a phase where the wave is attaining maximum. Means phase is basically angle. There is a phase where wave is attaining maximum. There is a phase where the wave is attaining minimum. So if you are able to join all those phases, right? If you are able to join all those phases and get a shape, that shape is what is called as wavefront. Let me explain it. See, suppose I have a point source of light. Imagine this as a laser source. Okay. Now, what will happen is light is getting emitted. We will not be able to see this because, first of all, the frequency is not this small. It is very high. They are very close to each other. Okay. Now, it starts emitting the light in all the directions. Can I say it like this? Now, I have a specific phase. Means I'm taking a phase where the wave has attained maximum for the second time. So on the first wave, second, third, fourth, fifth, sixth, seventh, eighth, like this if I take, and join all these points. When I join all these points, I'm getting a shape. This shape is called as locus. You have heard this word locus? For example, circle is a locus. So you have to define a circle. Circle is locus of all points which are equidistant from a fixed point. You have to understand. Similarly, for wavefront also what you do is if you take the points which are at the same phase and join all of them together, the shape that you get is called as a wavefront, right? And that wavefront depends on how the source of light is. In this context, if you see what is the shape you are getting, it is actually not a circle, it's a sphere. Because light can get emitted in 3 dimensions. We could draw it only on a 2 dimension, so it is appearing like a circle, but it is actually a sphere. So due to a point source, what is the wavefront generated? It's a spherical wavefront. But before the shape, are you guys clear with what is wavefront? So I'll explain it. See, the locus of all such points which are oscillating the same phase is called as wavefront. That every crest or trough is a wavefront. Okay. So if I have to give a proper definition to it, this is how you define. Wavefront is defined as the continuous locus of all such particles of the medium which are vibrating in the same phase at any instant. So at a given time frame, if there is a particle vibrating in a particular phase, you call that as a wavefront. Am I clear with this point? Okay. So basically, how do you define wavefront in another context? It is a surface which is of constant phase. So the speed with which the wavefront moves outward from the source is also called as the phase speed. It's also called as the phase speed. Here. Shall I proceed?
Yes, sir.
So now we are going to see the classification of wavefronts. So there are basically 3 classifications. One is called spherical, second is called cylindrical, and the third is called, I think it is called repeated. Third one is called a planar wave, plane wave. Point got repeated. Okay. So in this chapter, we'll be discussing only about 2 types. One is spherical, and the second is about plane. Cylindrical, we generally don't use. So for spherical wavefront, I already explained you the concept. So in the case, waves are traveling in all the directions from a point source. The wavefronts are going to take the shape of a sphere. Okay. This is why is this happening? This is because all such points which are equidistant from the point source will lie on a sphere, and the disturbance starting from the source S will reach all the points S simultaneously. Will reach all the points simultaneously. Means they are trying to indirectly tell you that the wave will start traveling in all the directions with the same speed. The meaning of the statement is speed of wave is same in all directions. Okay. Next, this is cylindrical wavefront. So you'll be able to get a cylindrical wavefront if you have a linear source. So this is because the locus of all such points which are equidistant from the linear source will generally take the shape of a cylinder. And the last one is called as plane wavefront. And for the plane wavefront, the source of light should be at infinity. And the source of light is at infinity. The kind of wavefronts you can define for them is a plane wavefront. Okay. So we saw what are wavefronts. Is there any doubt till this point? You're clear, right? The counterpart of wavefronts are called as rays. The rays. RAYS. So what is a ray basically? If you have discussed the previous chapter, what is a ray? Ray is a one-dimensional shape which has a starting point but no ending point. Okay. But that is mathematical definition. What does a ray have to do with respect to a wavefront? Now what we are actually trying to do is, when you deal only with wavefronts, it is difficult for us to analyze certain situations. So you definitely need the help of some other geometrical shape which is simple. For that, what they did is they combined the wavefronts with the concept of ray. So ray is basically an arrow, no doubt in that. But how is that arrow drawn with respect to a wavefront? It is always drawn perpendicular. Means if I give you a wavefront and I ask you to draw the ray for it, what are you supposed to do? You need to draw an arrow mark perpendicular to the wavefront. And once you draw them perpendicular, you should also mention the direction in which it is moving. So how will you show it? With the arrow mark. Prida. So what does a ray of light represent? A ray of light represents the path along which light is going to travel. Okay. The next one is principle. So what is the first principle? Rays are always perpendicular to wavefronts. Rays are always perpendicular to wavefronts. The second point is, time taken for light to travel from one wavefront to another is the same along any ray that you take. I'll come to that. Listen to this carefully. If I have spherical wavefront, which is getting generated due to a point source, if this is the source, then the rays are going to travel in this way. Are you able to understand this point? So if I take this as A and this as B, if you measure the speed of the light along, if I call this ray as 1, and if you measure the speed of light between point C and D along the second wave, they are saying it will be the same. Read that point. What did they say? Light travels from one wavefront to another along every ray with the same speed. So you understood how I drew the rays? Because I drew perpendicular, right? So if you measure the time it takes for the wavefront to reach from point A to B. So A to B means along which rays direction did you measure? Along ray number 1. Similarly, if you measure from C to D, which you are measuring along ray number 2. Okay. So they are trying to say whatever time it takes for the wavefront to go from A to B will be the same time taken for the wavefront to go from C to D or any other wavefront. Is that point clear? So this is a very, very, very important point. Because based on this, we are going to prove laws of reflection and refraction. So, yeah. Similarly, in the case of plane wavefront, whenever the wavefront is planar in nature, for plane wavefront, you will have set of parallel rays. Whereas in the case of spherical wavefront, what will happen? The rays will either converge or diverge from that point. So if I have a spherical wavefront, okay, the rays can either get converged or they can get diverged as well. Clear with this, I'll proceed to the next one. Shall I proceed? Okay. So the next important concept that we are going to discuss is Heightens principle of secondary wavelets. So if you ask me on what basis the wave theory of light is framed, it is based on Heightens principle. So what does Heightens principle mainly speak about? It mainly speaks about how wavefront propagates through a given medium. So it mainly speaks about how a wavefront actually propagates through a given medium. Okay. So this principle is based on the following assumptions. Now, whatever points I'm going to tell you is also sometimes referred to as Heightens construction. Is referred to as Heightens construction. So you remember in your 10th grade you would have learned how to draw a tangent, how to draw two tangents to a circle using compass and all those things, scale and all those things, right? In a similar way, this mainly speaks about how wavefronts are going to travel. And for that, what are the steps you are supposed to follow in the construction methodology? Okay, the first one is, so if you look at the topic, what is it telling you? It is telling the Heightens principle of secondary wavelets. It is not using the word wavefront. Is it using the word wavefront? No, it is using the word wavelet. I'll explain the difference. Okay. So generally, when you take a wavefront, wavefront is basically what? Wavefront is the locus of all points that are formed. Wavelets are basically the locus of all points that are vibrating in the same phase, right? Now, if you take each point on the wavefront itself, so what they are saying is, for example, if you take a spherical wavefront like this, let's say this is the first wavefront. So each point on the spherical wavefront will start acting as a source for the next wavefront. Means, see, actually the first wavefront itself has got generated due to a point source. Is that right? First wavefront got generated due to a point source. What will happen is, on this wavefront, if every point starts acting as a new source, then there will be another wavefront getting generated due to other Suprakara. Each point on the wavefront acts as a fresh source of new disturbance, and the fresh source is called as secondary waves or wavelets. So, due to this point source, if this is a point source, if you treat it exactly like how you treated this S, then what should have happened? You should have had a spherical wavefront around that source on the wavefront. Breathe up. So this would have generated a new wavefront. This second one, this would have generated a new wavefront. This would have generated a new wavefront. Actually, the new wavefronts which are generated due to whom? Due to each point on the wavefront are actually not called as wavefronts. They are called as wavelets or secondary wavelets. புரியுதா நான் சொல்றது? Okay. Now the question is, how do these secondary wavelets start traveling? They start traveling, that is, they start getting spread out in all directions with the speed of light in that medium. So whatever is the speed of light in that medium, for example, if this is happening in water medium, whatever is the speed of light in that water medium, these secondary wavelets will start spreading outward with that speed. புரியுதா? இது வரைக்கும் ஏதாவது டவுட் இருக்கா? அது கிளியர்? புரியுதா இல்லையாடா? Now what will happen is, if you draw a tangential surface to these wavelets, so in the wavelets, if you draw a tangential surface, then you get a new shape as a whole. That new shape is what is called as the new wavelet. Means the second wavelet is actually formed because of this kind of a process happening. So simpler, so what are the steps now? First, initially, what is happening? The source, the major source will, the basic source will start producing. Need not be a point source, any source. It produces the first wavelet. Do not call it as primary wavelets. This is a wavefront. Each point on the wavefront acts as a phase source for the next wavelet. Wavelets. They are not wavefronts at all. That is what I'm saying. Yeah, secondary wavelets. You don't use our primary wavefronts at all. They don't even exist. This is the theory he proposed. These wavelets do not exist. He's trying to say that they act as a source for the new disturbance, because you need to give a theory to it. There is nothing like primary wavelet. Where do they use? There is nothing like primary wavelet. Primary is called wavefront only. That's not called primary. It's called secondary wavelet. The secondary wavelet. So this is the secondary wavelet of the first wavelet. Again, what will happen? The second wavefront is generated. On the second wavefront, again, what will you have? You will have infinite number of sources, and the infinite number of sources will again start producing wavelets. Upon the wavelets, the tangential, if you start joining them, you will get the third wavelet. Point about it. It's spread. Okay. So the new wavefront at any later time is given by only the forward envelope. It doesn't give you the reverse envelope. Means you don't draw the tangential surface to the bottom. You draw a tangential surface only to the outer part. Okay. The new wavefront at any later time is given by the forward envelope, that is the tangential surface, the forward direction of the secondary wavelets at that instant. Is that clear? Okay. So with respect to this, on this basis only, what we will do is we will explain the concept of reflection of light and refraction of light, which I'm not going to explain now because I've done a separate video on this. That will be clearer for a 7-minute video each. 15 minutes if you can concentrate. I've clearly explained how to convert these steps into a diagram. Then I have used a compass or a meter. You come for tomorrow's class, then I'll explain. So yeah. So this is all about wave theory. So this is all about wave theory. So reflection and refraction, I'll add those 2 videos in the app. Just go through them. 1 minute. The next topic that we are going to concentrate on is principle of superposition of waves. So this is not a new concept. Principle of superposition is already known. When do we speak of waves? Basically, when you have a number of waves, right, there are multiple waves traveling through a medium. They superpose on each other. What do you mean they superpose? They overlap or they come in contact. If they superpose on each other, then there is a resultant displacement that is going to arise. So the resultant displacement at any point, at any point at a given instant, means if two rays are meeting at this point, so at this point, at the given instant, what will happen is there will be a resultant displacement, which is basically expressed as the vector sum of the displacement due to the individual waves. Due to the individual waves at that point. So if I have to observe it mathematically, then what can I say? If y1 vector, y2 vector, y3 vector, so on till yn vector are the displacements due to the different waves acting separately, then according to principle of superposition, what can you say? The resultant displacement when all the waves act together at a given point are given as the vectors. So if you observe them clearly, they will write it as scalar, the bar of so y vector should mathematically be equal to y1 vector plus y2 vector plus 1 till yn vector. Right? I hope this concept is clear. Next is when two superposing waves are in the same phase. When two waves are in the same phase, then what will happen is crest of one, that is the highest point of one, will match with the highest point of second. So at that point, you think the addition will intensify the situation or nullify the situation? Intensify, because maximum and maximum are coming in contact with each other. When this happens, when the crest of one falls over the crest of the other, or the trough, that is the base of one falls over the base of the other, then what happens? Here also, if you see, the situation will get intensified. Because from this nothing but it is also amplitude, but in the negative direction. Is that correct? It's a fear. So their displacements get added. But if one crest is meeting with the crowd, then what will happen is they will get nullified. In the sense, the intensity gets cancelled. Are you able to visualize the situation? I'll show you a simulation. Shall I proceed? The next concept, which is an extension of principle of superposition, is interference of wave. So basically, when you see interference, right? Interference is superposition wave. So when two light waves, so here there are certain restrictions that are there. When you talk about principle of superposition, you have to speak about frequency, wavelength, all those things. Two waves are there, they're traveling in a medium, they superpose on each other. What is going to happen? Whereas the same principle of superposition has to be called as interference of light. There are specific conditions that need to be taken. So when two light waves of what? Of the same frequency, when two light waves of the same frequency and having zero or constant phase difference. So what is happening basically? When two light waves of the same frequency or those waves which are having zero or they can have a phase difference. They're not saying the phase difference has to be zero, but the phase difference between them at every instant should be a constant value. Means, for example, if the phase difference between them for 1 second is, let's say, pi radian, for the next 2 seconds, it should not become pi by 3. It should be the same pi. Okay. If at all this kind of a situation occurs, then these kind of light waves are also called as coherent sources. called as coherent sources. COHERENT. So what are basically coherent sources? Those waves which have the same frequency and zero or constant distance. They are called as coherent sources, which are traveling in the same direction. Again, if you observe for interference of light, another important point is both the light waves should travel in the same direction. So if they travel in the same direction and superpose on each other, then wherever they are getting superposed, in that region, the intensity gets redistributed. Where the intensity will be maximum at certain points and the intensity will be minimum at certain points. And this kind of a phenomenon is called as interference. Shall I proceed? Yeah. Actually, where is it? We're coming over last week only. Wait for this. Succeed. if I have two light sources like this, okay. Let's say one drop of water is, you're able to see the ripples started traveling, right? So if I add another source to this, see what is going to happen.
Sir, I can't see the simulation, sir.
1 minute, 1 minute. Now you're able to see.
Yeah, yes, sir, fine.
So what you have to do is reset. See, one drop of water, I mean, one tap is on, the wavefronts are continuously traveling in a circular path. When the other one is also getting joined, look at the pattern. None of them are able to completely maintain the circular paths because the way they are meeting at certain points is changing. So you're able to see, observe some, I'll make it slow, see. You're able to see some brighter spots. No? The brighter spot is a place where the waves in same phase are interfering. That is, the waves in same phase are superposing. Whereas you're able to see some dark spots here. These dark spots are the places where the waves which are out of phase are superposing. Out of phase now, one is maximum and the second is minimum. When this kind of a scenario occurs, then we see something like this happening. Right. So this is what is called as interference of light. Now I can replace the same thing with laser source. So if you see, due to a laser source, light is going to travel in this way. Let's say it's a green color. If you want, you can change the frequency also. Let's say it's a red color or orange, whatever it is. So you're able to observe. Now what will happen is, if I place a screen, then see what is happening to the screen. This happens. It's not about straight line. You're able to see some spots are bright and some spots are dark. Because the light is not able to travel beyond that. So it has to get stuck there. But there are certain bright spots going and falling at a particular location. If I make this process slow, see all the dark spots are going and falling and they're creating a pattern on the screen. Okay, these are called as, actually the pattern that you see on the screen are called as interference fringes. Okay, so technically what is happening in the back end is, when waves of same frequency, waves of same phase superpose, it is giving the bright spot. When waves which are out of phase are getting superposed, I'll not say wave, I'll say portion of the waves which are out of phase are getting superposed, you're able to get a dark spot. Is this point clear, guys? Right? Now our job is to find out, where do you get that bright spot? Where do you get the dark spot? But before that, we need to understand a concept called as constructive and destructive interference. Okay? So write down the next heading as constructive and destructive interference. Okay. So write down the heading as interference of two light beams, and in the bracket write it as constructive and destructive interference. Okay. So one point you can notice, if the crest of one wave falls over the crest of the other wave, or the trough of one wave falls over the trough of the other wave, the amplitudes of the two waves get added up, and hence the intensity becomes maximum. Similarly, so this you can call it as constructive interference because they've got superposed to develop maximum intensity. The laptop got switched off. Power it up. The whiteboard also. Okay, now we are able to visualize this. Now one drop will get fallen over the other. It forms a destructive interference. Is it right? Sure, your laptop. Okay, no? Clear. So this part I'll tell you how to derive the value of constructive and destructive interference patterns. See, I told you constructive and destructive interference are applicable for two coherent light sources. So what is, if first wave is written as y1 is equal to a sine omega t, then second wave can be written as, I'll write it as a1 sine omega t. The second one I'll write it as a2 sine of omega t plus phi. Okay. So principle of superposition says y is equal to y1 plus y2. Here I didn't follow vectors is because when you talk about interference, both the light waves travel in the same direction. So y1 plus y2, which implies it is a1 sine omega t plus a2 sine of omega t plus phi. So how much will this be? A1 sine omega t plus a2 sine omega t cos phi plus cos omega t sine phi. So if I take out sine omega t outside, I'll have a1 plus a2 cos phi plus a2 sine phi or a2 cos omega t, or I have a2 cos omega t sine phi. Is it clear? Now what I'll do is I'll take this a1 plus a2 cos phi as some capital A cos theta and a2 sine phi as some capital A sine theta. When I do this, when I take and substitute them here, what do I get? I get a cos theta sine omega t plus a sine theta cos omega t. Right. So what can I take out common? A into Sin omega t cos theta plus cos omega t sin theta is actually sin of omega t plus theta. Is that clear? Is it clear? Now listen to this. Let me call this as equation number 1. Okay. This is the equation of the resultant wave. This is the equation of the resultant wave. You can copy it. I'll give you time, but observe. So from this data, what can I say capital A is? So A1 plus A2 cos phi is capital A cos theta, and A2 sin phi is A sin theta. If you square and add them, what will you get? A1 square plus A2 square cos square phi plus 2 times A1 A2 cos phi plus A2 square sin square phi is equal to A square into cos square theta plus sin square theta, which is going to give you 1. Okay. Now you will have A1 square plus A2 square, combine these two, plus 2 times A1 A2 cos phi is equal to A2 square. Sorry, is equal to A square. So what will be the value of A? A will be root of A1 square plus A2 square plus 2 times A1 A2 cos phi. This is point clear. Right. Now see, A is the amplitude of resultant wave. Right. So if amplitude is maximum, intensity is maximum, because intensity is directly proportional to amplitude square. Right. If you observe this mathematical equation, who is deciding the maximum or minimum value of amplitude of resultant wave? It is this cos phi. If cos phi is equal to -1, then amplitude is least. Then phi will be how much? Phi will be odd multiple of pi. Means if the phase difference between two superposing waves at a given point is odd multiples of pi, at that point you will have destructive interference. In a similar way, if cos phi is equal to 1, then phi will be equal to 2n pi. So at this place 2n pi, you will have constructive interference. Is it clear? So these are the two important mathematical conditions after which we need to understand. Another concept is also there, which is called as path difference, about which I'll explain tomorrow. But you can copy it till here. Did you finish this slide? So we'll wind up with this. The remaining topics we'll see tomorrow. Actually, we take one little fast. Generally, I take this topic for at least 40 minutes. You projecting level faster than you're not confused. Okay, those are online. Are you clear?
Yes, sir.
Okay. Okay, then we'll wind up.
Thank you, sir.